All right, so welcome to the Asteroids and Comet session, and by comets I mean comet session, where talks are
Total 15 minutes.
12 minutes with 3 minutes for questions. We will give speakers a 3-minute warning, and then there will be a stop, and then if you want to keep using your remaining 3 minutes for talking, you are more than welcome to. With that, I guess this is Julie Brisset.
Good morning to the hardcore small bodies people. Everyone else is at the moon session. Well, this is still ongoing. There's, as Eddie just mentioned, there's awesome missions on their way. So, okay, so at UCF we have a microgravity lab, and we perform like all types of experiments. But today I'm going to be talking about the ones where we poke very gently a surface of a simulated regolith and look at what happens. And so this presentation is about new results on old data. And here are the hardware setups that we use called Prime and Collide. And you can see that data collection goes all the way back to the 90s. And so this data is always collected in microgravity, so it takes a long time to prepare the payload, a long time to fly it, and then do the data analysis. But as we speak, we finally have a good data set that we can do things with, and so we regularly find new things in this data set, even though the data has been around for a bit. So here's a picture of the Prime setup. So this experiment gets bolted to the parabolic aircraft, and you see these individual boxes. It vibrates, but it doesn't point. So you see these individual 4 boxes here, there's 4 more on the other side, and in each box we have a rather simple setup. We put Regolith in the tray down here, or simulated Regolith of course, and then from the launcher up here we launch spherical impactor, and then we watch the impact with a camera looking like this at the box. And the box can be removed from the setup so that we can perform the experiment in really good microgravity conditions, free floating. And the type of simulants that we have in the tray are quartz sand and lunar simulant JSC1. Down? Okay. I'll just... Oh, and then okay. And then, so our impactors, as I just mentioned, is 2 centimeter sized spheres. And the speeds we're talking about, so the gentle poking happens here in the setup 15 to 50 centimeters per second. And so this setup flies on parabolic aircraft, and we have a very similar setup that flies on suborbital rockets. So same concept here. We have a tray at the bottom where we put our regular simulant, and we launch a projectile from the top. Here, in addition to quartz sand, lunar simulant, we also used Mars simulant. The impactors are the same, just a bit of a larger impact speed range, and this setup flies on suborbital rockets, so it has to be a bit stronger. As you can see, the vacuum box here is a bit rougher. And so this is kind of data that we get. So that's an impact of about 20 centimeters per second into a bed of quartz sand. And you see here in the box is free floating, and we have a nice ejecta plume after the impact. And if we perform the same impact with lunar Regolith simulant, we have a very different outcome. So instead of an ejecta plume, we have almost no ejecta here, and we have now, and that's new, a rebound of the, or you can actually hear Josh talking in the background. So you have a rebound of the projectile, and so very different outcome for a different Regolith simulant. And so if we plot all these, all the data that we collected since the 90s, we get this very complex plot. So here I have the mean ejecta velocity versus the impact velocity, and so all the impacts that did not produce ejecta are plotted down here. And so the colors show you the different residual acceleration environments. When the box, in older setups, the box was bolted to the aircraft, and so you still had 10 to the minus 2 G going on inside of your box. But the free-floating box, which are the black points here, you see you can actually reach lower impact velocities, and then now you have a 10 to minus 4 g maximum acceleration environment. So red color is the lunar type of gravity level, and the black dots are more like small asteroid type gravity levels. Then we had the three types of simulant. So the filled boxes are the lunar simulants, the open symbols are the sand targets, and then these green crosses are the Mars 1 targets. And then we had four types of outcome, because we had either ejecta or no ejecta produced, and either embedding of the projectile, so the projectile goes into the target and stays there, or it rebounds. And so just a few things about this this data set, basically, that we can see here. So first, the Mars 1 simulant behaved similar to the sand grains, and the lunar simulant behaved differently. So you see the filled boxes up here. Their ejecta velocity has a very different power law than the group of the open symbols. And so when you look at with the microscope at the Mars 1 grains, the Mars simulant grains and the sand, they're all a bit rounded, whereas the lunar simulant grains are very angular. So you can see the difference here. And then another important thing to see, under 10 centimeters per second, we don't produce ejecta ever. We only see ejecta production starting here, and actually it's not shown here, but the black dots is very little ejecta, and you start having ejecta plumes starting at 50 centimeters per second. And then finally, and very important too, there is no rebound in lunar gravity levels. The rebound was only observed in asteroid gravity levels, so very low gravity levels. Okay, so this is the data that we get, and what I want to talk about today is coefficient of restitution and penetration depth. So coefficient of restitution, we plotted, so for the impacts that had, when we could observe a rebound, so in asteroid level gravity, we plotted the coefficient of restitution of the regolith bed towards the impact velocity. And we see, here's collide data, maybe you can't see so well, but the green points are collide data, and the prime 3 campaign points are here, and you see as you go under 10 centimeters per second, you get really an increase in the coefficient of restitution, and really think that shows that the energy of the impact actually does not get dissipated in the bed of regolith as well, because now you don't lose you don't create ejecta. All the energy, I mean, not all of it, but more energy can go back into the rebound of the projectile. While when you have ejecta production, you end up having a very low coefficient of restitution. So you have a transition between no ejecta and ejecta production here between 20 and 30 centimeters per second impacts. And so we wanted to compare these results to experiments that were performed in 1G. So I just said there's no rebound in lunar gravity. So how did they do that in 1G? Well, they put their target perpendicular to the G level, and they shot at it horizontally. And so what they see, and of course they have higher energy levels that we can do in our setups. And what they see is the coefficient of restitution of their regolith bed. Oops, can I go back? Yes, yeah. Perfect. What they see is the restitution coefficient scales with the impact energy with a slope of minus a quarter. And so we don't see that. So here's the same plot with our data. And instead, so actually, if we take all the points together, we see the same kind of scaling, but instead we see actually two families of data points. And here in the collide data, we didn't really see any influence of the impact energy on the coefficient of restitution, but for the prime ones, we saw double the slope. So here the problem is for collide, for collide we have very low resolution data, while we can see much better what's happening up here. So the conclusion of it is we have to get more data to see what's going on with the coefficient of restitution. Okay, so projectile penetration depth. So for each impact, we can also measure how far in we can reach with our projectile. And again, looking at 1G experiments, they got, so Vmax is the maximum penetration depth of their projectile into the sample. They got a scaling with a slope of 1/3 with this quantity here with the total travel length of the impactor. And the total travel length includes the drop length in 1G and in addition to the penetration depth. But when we do that, of course, in microgravity, we don't have a drop length, but we can have an equivalent, through the energy, we get an equivalent drop length. We don't really see a scaling with 1/3. So looking more into literature, we found this paper, they scale it with this quantity here, and that scales. Now, the penetration depth into a layer regolith scale with this quantity. So what's that? So here we have the friction coefficient of the target bed, the ratio of the projectile and the regolith density. We have the projectile diameter, and we have a quantity here, which is the total travel length, but it actually just is the impact energy plus the penetration depth. And in color here, in blue, I have the parameters that are tied to the target, and in red, the parameters that are tied to the impactor. And so if we try to scale our results with this quantity, we actually do see a scaling law, but we had the data split in 2 data sets. And so the lower mass impactors, the higher mass impactors. And so if we actually just change our projectile here, our density ratio, if we change the factor there, we can collapse the data into just one power law. So this means that now we're scaling with this quantity here. And so, and a factor of 2.5 added to the whole thing. So what does it mean? So now our density ratio, it plays a reduced role in the depth that we're going to go into the regolith. Our friction coefficient, it plays a more important role. So if you have stronger cohesion in the grains, you will less be able to get into the regolith bed. We have an increased role of the diameter of the projectile. Smaller diameters will be, you get easier into the projectile target. I have to stop. No? Okay. That's the end. So the results we get, so in our data, we see that we have a dramatic increase of coefficient of restitutions on regolith beds in microgravity for impact speeds 10 centimeters per second, lower and lower. And so very slow impacts will be very bouncy. So here I have a picture of the Philae lander who actually bounced off the surface of a small body. The projectile penetration depth is significantly affected by the gravity environment. So the target resistance to penetration, it will be more important on a small body because the friction forces will be more important than gravity. The role of the projectile diameter and the energy of the impact will also play an increased role in how deep you can go into the surface of the small body. And so just like Eddie this morning, I could not resist to put this picture up. So Hayabusa 2 just arrived at Bennu, and just to sorry. It does look the same. Okay, yeah. So if you apply the scaling law that I showed earlier and you estimate some numbers for these 2 spacecrafts and their expected impact speed, you get here an estimated penetration depth, which is of the order of a centimeter onto the surface. So don't take these numbers too seriously. I had to estimate like the density of the sampling arms and things like that. But the difference that you see here, that Hayabusa 2 is actually penetrating almost 3 times more than OSIRIS-REx on Bennu. It's the diameter of what they call the horn here, and of the taxam on OSIRIS-REx that makes this difference. Anyway, thanks for your attention. Sorry for talking so long.
Time for one question. All right, maybe.
Oh, sorry.
All right, I guess it's Umberto.
Quick comment.
Questions, Umberto.
Hayabusa 2 will have a number of deployments. I think it's up to, no, it's like 10 total because they send probes.
Yes, okay.
So you will
But I
be able to
calculate for the
sample.
horn. I calculated only
Right,
for this
right.
horn.
But
yeah.
you may, if they have the data, you may be able to sample the different terrains that because they're going to have several deployments. So in that sense, they're going to give you a lot more data than OSIRIS-REx.
Yes.
All right.
Thanks.
Thank you, Julie. Our next speaker